associate at Indian Institute of Science, Bangalore, and he was also postdoctoral fellow at Ismail Institute of Science, Israel, Physical Research Laboratory, Ahmedabad, and he was a project officer at Indian Institute of Technology at RUS, Chennai. His research interests are in nonlinear dynamics, chaos, quantum information, and quantum optics. And we'll be talking about thermalization and quantum chaos. So, Dr. Chethil, on to you.
Thank you for your introduction. Okay, so let me share the screen. Are you able to see my screen?
Yes, yes.
Yes, good morning, everybody. I'll be talking about chaos in quantum systems. So specifically, I'll be talking in multi-parted system, because this problem is more than 20 years now. People have been discussing about quantum chaos. So I will give you a brief introduction. Then I will, because this is basically the recent advances in quantum chaos, basically comprising what are the tools people look at to understand quantum chaos. So here, so there are various measures to understand chaos using observables or quantum Fisher information, random matrix theory, eigenstate thermalization hypothesis, adiabatic gauge potential. So these are different methods to understand quantum chaos. So I'll be explaining each of these things with some specific examples or some theory. So we know that chaos is having a lot of applications, because starting from the weather predictions. So because it is a very important concept in nonlinear dynamics. So all of you know that so in classical chaos, if you have two initial conditions, they are very close to each other. And if the system is having a chaotic property, then what happens is when time goes, these two initial points in the phase space separated will get separated exponentially. So that is the basic concept of chaos in classical systems. Obviously, this is actually the basic theory also for even for quantum mechanics systems in quantum system for quantum systems. So, but the problem is when you go to the quantum system, because the basic equation, which is the Schrodinger equation, which is basically linear. So because one of the important aspect to have the chaotic property is that the equations governing the dynamical variables should be nonlinear. So, but Schrodinger equation, we know that it is not a nonlinear equation. So now we have to, because obviously, because the classical systems is only a limit of quantum systems. So obviously, what we see it in classical systems, we should be able to see it in the quantum systems also. So we have to think in different ways to understand chaos in quantum systems. So in classical dynamic systems, actually exhibit lot randomness ranging from mere ergodicity to fully developed chaos. And evolution, whatever I said earlier, the evolution equations for the dynamical variables describing the behavior of chaotic systems are necessarily nonlinear. In quantum dynamical systems, evolution equation is governed by Schrodinger equation, which is inherently linear. It is not straightforward, therefore, to access the extent of random terms in a quantum system. So then the main job is to understand the ergodicity or chaotic properties of quantum systems in terms of some signatures in quantum mechanics. So identifying signatures of the nature of the ergodicity of the quantum mechanical counterpart of a general classical systems. So I'll be discussing, so that is one of the methods I'll be discussing later. So identifying signature of non-classical effects in the temporal behavior of quantum mechanical expectation values. So even though there is no, because the phase space, because there is an uncertainty principle, so we cannot have the phase space concept for the dynamical variables. So, but still we can have some kind of analysis based on the expectation, because we have the expectation values for each variable, even though there is an uncertainty for each variable. But we can use that expected value and we can make that as our phase space variable, and you can do the analysis. So that is the first thing I wanted to discuss about, how we can make use of the expectation values or average values of observables to understand certain quantum systems. We may not be able to do that analysis for all the systems because of some constraint or some difficulty. So, for example, consider the simple one-dimensional example of particle of mass m subject to potential V of x. The Hamiltonian is given as this, so the Ehrenfest theorem says that the derivative of the expected value, derivative with respect to time for the expected value of x is equal to, means proportional to the average value of the p, and average value of p is equal to the average of minus del v by del x. So for quadratic Hamiltonian, what happens is the second equation is simplified to this dp by dt is equal to just minus del v by del x. So this expectation values, so this simply for a one-dimensional system, so that there is only one x and p. So these expectation values follow the classical motion. So for non-quadratic Hamiltonians, classical motion arises only if the potential can be approximated to the quadratic form. So this is the important aspect. If your Hamiltonian is quadratic, you get you can actually get that classical motion. But if the potential is non-quadratic, you cannot have that kind of relations, that kind of equations for x and p. So because if there is a non-quadratic Hamiltonian, what happens is because in the quantum systems, suppose you take some wave packets, already some talks has been, earlier there were some talks regarding coherent state and different types of quantum states people deal with. They are all actually the wave packets. So because you know the wave packet is basically the superposition of so many states, basically superposition of the basis states. And when you have this non-quadratic Hamiltonian, that actually spreads in time. So from the expected value or the average value of the observables, we can actually understand whether the system is periodic or not very easily. Because what you have to do is you have to take these expected values and plot them in time. Then you can see that if there is a periodic, they will repeat in periodic intervals. So this basically you can, using the fidelity of the overlap function between the state at time t and state at time 0. And you can see that at certain times it can come back, because then this fidelity will, or the overlap function will become 1. So if that is happening regularly in time, suppose the fidelity of the state at any time t is becoming, with respect to the state at a time t equal to 0 is becoming 1 at a regular interval, we can say that that system is periodic. So in the classical phase space, this will be, suppose you plot the expected value of x and expected value of p, then in the classical phase, this will be a closed trajectories. So now, this kind of the periodic things are actually in the case of the wave packets for the non-quadratic Hamiltonians are considered as revivals, because there is a spreading happens initially and later on they comes back together. So it is one of the non-classical phenomena in condensate optics that is called a revival. And so there is also something called a fractional revivals. So I will not be getting into those things now, but my main concentration is on these dynamical properties and quantum chaos. So there is when the wave packet spreads and between revival and the initial time, what happens is this state at certain times can be a superposition of wave packets which actually resemble the initial state. So that is actually called the wave fractional revival. That's just for something I just want to talk there now. I will not be getting into that. So the effective Hamiltonian for propagation of single mode. So earlier we said that if there is a periodic behavior, obviously the fidelity of the state at any time t becomes 1 with respect to the initial state, and all the expected values will come back to the initial value at the periodic times. So for example, consider this Hamiltonian, which is actually models the propagation of single mode field in a Kerr medium, which is equal to h cross chi a dagger square a square. So a and a dagger, all of you must have heard about. These are all creation and annihilation creation operators, and which is equal to h cross chi n into n minus 1, where n is a dagger a. That is the number operator or photon number operator. Okay, and a dagger obeys the commutation relation 1. So this already you know the coherent state definition role. I will not be getting into that. So suppose you take the coherent state and you take that Hamiltonian, find the unitary operator, and you do the time evolution, and you can calculate state at any time t very easily for that Hamiltonian analytically. You can find out, and you can see that that states have a periodic properties or revival properties at certain instance of time. Similarly, the expected values, for example, consider the operator, position operator, and the momentum operator, and you find out its expected value, and here x0 and p0 are the initial values of this position momentum. So under this Hamiltonian, you can see that this again, there is a periodic, you can see that x and p periodically comes back to its initial value. And if you plot x versus p, what you get is a closed curves in the phase space. So this is a very clear way we can understand the periodic systems. So the Hamiltonian we discussed earlier, that is h cross chi a dagger square a square. We can have some classical counterpart for that. That we can write it as in the square plus p square whole square form. But here you can see that it is not a quadratic Hamiltonian, and the frequency of the motion is actually depends on the initial conditions. So that is one important aspect here. This Hamiltonian in the classical counterpart is having a this Hamiltonian, and its frequency of motion depends on the initial conditions. That is not usually happens in the other harmonic oscillator case. So here, if you in the classical equations, if you substitute again, you can see you can get the inverse theorem, whatever you did have earlier. some equations like that, but only difference is this nu is depends on the initial condition, that is the frequency. So one just relate this periodic orbits with the uncertainty product. You can see that, for example, this I don't know whether you have heard about this. Then somebody has talked about photon and coherent states. So these are actually when you act the creation operator on the coherent state, you get a one photon and a coherent state, and if you create 2 times, you get a 2 photon and coherent states, and so on. And so m is equal to 0 corresponds to the coherent state, and if you plot delta x delta p versus time, so what you can see that this red dotted one, I hope you are able to see that, and that one starts at some point and comes back to the same point, and it repeats in time. So for m is equal to 10, you can see that for 10 photon and a coherent state, this uncertainty products. There are some variations in between, but still it comes back to the initial point and it repeats. So this is a clear periodicity. You can see it in the observables, expected values of the observables. Okay. So now suppose you want to see something which is not periodic, but non-periodic. Okay. So obviously we have to think about some Hamiltonian, which is different compared to what we had earlier, and see something we can do. So for this purpose, we can look at explicitly the Hamiltonian for a single mode field interacting with a nonlinear medium. So here A corresponds to the atom field modes and B corresponds to the atom modes. And you can see that this corresponds to the nonlinear term. So this is the nonlinear parameter gamma. And this is the interaction term between the atom and field. And G is the interaction Hamiltonian. These mode operators obeys these commutation relations. For this, still there are the eigenstates are basically the number states, and you can consider the basis states as this in this case. So I will not get into the calculation here. I will just state the results here. So what happens is you can actually solve this equation numerically after some certain analytical calculations, and you can find out the state at any, so or the density operator at any time t, you can find out analytically you can find out, and if you really want to plot something, you have to do that numerically. And so here this is the plot of for weak nonlinearity, that is gamma by g is very much less than 1. That means gamma is the strength of the nonlinearity and g is the interaction strength. So if it is very weak, so you can see that this entropy is the von Neumann entropy. So this versus the time, this is both von Neumann subsystem von Neumann entropy is the subsystem entropy. Both are plotted here. For a system 10 photon 10 for first plot is for initially the field is in Fock state 10 and atom is in the ground state, and right hand side graph is for the field is in the coherent state and atom is in the ground state. So you can, in both cases, you can see that at certain time, say for example 600 plus here GT, this comes back, this entropy comes back to the same point, and it actually repeats. Okay, so this situation repeats when you increase the time. So here, what you can expect is that this also have a some kind of the periodic behavior. Same thing happens for if your field is in the coherent state. This also repeats in time. But there are in between, you can see there are so many structures here. This is what the peak in the middle, the minimum in the middle, it actually corresponds to the fractional revival time, which I discussed earlier. and other fractional revivals. So I will not be getting into that. So now suppose you increase the nonlinearity. Okay. So if you increase the nonlinearity, and you can see that, so here the gamma by g is much less than 1. So 0.01 is a small nonlinearity. So again, the nonlinearity is small, but the thing is you changed the initial state. And for different new value, where nu is the mod alpha square. And here you can see that scenario changes compared to the previous picture. Okay, because both of these graphs are for same nonlinearity, and but only difference is you have a different state for these two. So this basically is, if you look at the quantum mechanics, the state plays a very crucial role. And like in the classical systems, you know that if you discuss about the one-dimensional particle, if you want to know the dynamics of that, obviously you have to know the initial position and momentum, right? So that is basically like the concept of state in the quantum mechanics. Because quantum mechanics is, you don't mention what is initial x and p. Basically, that is actually related to the state you are considering. Because in the initial position and momentum for a given state, you have to calculate the expected average value. So, but state is suffixed to 1. So here in the quantum systems, what you consider is the initial states rather than initial position momentum, because in general, any phase space in quantum mechanics is an infinite dimension. So just 2x and p is not sufficient, because for a coherent state, you know that it's an infinite dimensional Hilbert space, and you can have a expectation value of x square, x cube, and so on. You can construct any number of observables in this Hilbert space, and you can find out the average values of all of them. So in principle, your this one, the phase space will be infinite dimensional. So there is no point in saying what is the initial condition. So initial condition, when you mention, that means you mention the initial state. So if I know the initial state, I can all this infinite number of expected values you can calculate. So here you can see that when there is a change in the initial state, the entropy started behaving differently. So that means if there is entropy is coming to the initial values, that means there is some kind of a periodic or near revival, near periodic systems are there. And the nonlinearity increases, this periodicity goes away. So, so here, because whatever we do it in the classical dynamical systems, for that to understand the dynamics of the system properties, so we do some time series analysis, right? So the time series analysis consists of finding out the Lyapunov exponent and other mutual information, all those kind of quantities. So from the Lyapunov exponent, calculation is actually a quantifier for the chaos. So if it is a positive quantity, we say that the system is chaotic. So here, what you can see that in quantum system also, you can actually consider different initial conditions in terms of the nonlinear, in terms of the states. Okay. Also, you can consider different parameters in the Hamiltonian. Then let us find out, you can create a phase space or the time series for some observables, and you can do a time series analysis, so that whether we can actually find out the Lyapunov exponent and understand whether there is a chaos or not. So here you can see that this one corresponds to, we have considered different types of initial states. The problem we have been considering now, that is electromagnetic field interacting with the medium. So here the initial state, the field state is in the coherent state and the atom is in the ground state. And this is the one photon added coherent state and the field is in the ground state. The atom is in the ground state. And this is 5 photon added coherent state, that is the field state, and the atom is in the ground state. And this one is the increasing nonlinearity we are doing here. So initially gamma by G is only 10 power minus 2. That has gone up to 5. So you can see that in between there are certain points we increase the new value also. So new value is basically the alpha, ket alpha. The ket alpha is if you take the nu, that is the average of the photon number operator A dagger A, that is basically mod alpha square. That is called as a nu. So if you increase, basically if you have the new value, that is the average photon number in the field state is higher. So that is also another study has been done in this case. So when you increase the average photon number, also if you increase the nonlinearity, what happens? So for lower nonlinearity, for lower photon number, you can see that systems are regular. But when you increase the nonlinearity, and even for increase in nonlinearity, depending on the initial state for a given photon number, average number of photon numbers, you have the regular orbit, but things become chaotic when you have the larger lambda values. So when you increase further, you can see that for larger nonlinearity and larger, the states also become, because one thing you may be knowing that the ket alpha is a classical state, and ket alpha comma 5 or the photon added coherences are non-classical states. So when the non-classicality increases, so basically when you go from the left to right, this is the increase in the non-classicality. And so you can see that when you increase the non-classicality, when you increase the non-linearity, and also when you increase the average photon number, the system is becoming more and more chaotic. So that is one of the results we got when we have done the analysis using the observers. So this is the one method we can actually implement to understand the systems. But this analysis may have a drawback, because doing the time series analysis for a larger system and for the multi-part weight systems may not be an ideal one. So because you have to get the minimum embedding dimension, because if the system is actually in principle infinite dimensional, and if you want to get a minimum embedding dimension and all, we may have to deal with a very large number of data. Okay, so the understanding from here is, because there are something I want to quote, read from here. That is the Lyapunov exponents that characterize the dynamical behavior of classical and quantum expectation values of the same observer can indeed be very different from each other. So this observation is there because what you understand from the classical system Lyapunov exponent, and what you from the quantum mechanical expectation value, and from that time series and the finding the Lyapunov exponent, they may be completely different. Okay. So two interesting observations will be made in this context. In isolated quantum systems with a discrete energy spectrum, it can be established that Lyapunov exponents would vanish if computed from the time series data collected over a sufficiently long time. So if you collect the data for a very long time, and if you calculate the Lyapunov exponent, this Lyapunov exponent will get vanished. However, once measurement upon the system is included through appropriate interaction with an external system, the corresponding Lyapunov exponents need not vanish. This would suggest that, in principle, the dynamics of a subsystem as reduced from the time series data of certain variables may show exponential instability, even if the system as a whole does not. This is a very important concept. That is, full system may be completely integrable, and there's no chaos in that. But the subsystems, if you have more than two systems interacting each other, the subsystems, and if you calculate Lyapunov exponent for that subsystems, then what happens is that can show the non-linearity, because when the chaotic property. So that is basically like even a one system interacting with the environment. So this system you can consider as a subsystem, the other one is an environment. Okay. Or two systems interacting each other, and the one system in that, it can be considered as a subsystem. So that is what happened in our case here. This is basically the subsystem we have calculated. So its average values actually shows the chaotic behavior. So there is another study that recently we have been looking at is the whether different way of quantifying, which actually collaborate all our results, is possible or not. So one is the quantum Fisher information. So quantum chaos has been studied using intrinsic properties of the physical system, like the phase space carrying, spectral properties of the generating Hamiltonian, hypersensitivity to perturbation, and the decay of the fidelity measure, etc. So these ways quantum chaos has been studied. So there were many entropic measures to study quantum chaos, but which one was an appropriate quantum analog was not known. So you can see earlier I have presented the von Neumann entropy. So von Neumann entropy shows this kind of non-periodic properties when you increase the non-linearity. And so obviously there are different kind of measures for entropy. So which one is the best choice? That was not known. So using the quantum Fisher information, we studied the classical Fisher information in logistic map and found that classical Fisher information could sufficiently quantify chaos in classical systems. So you can have a classical Fisher information and you can study that. And if you from that, you can actually quantify chaos. So that is actually well established theory. So you can actually do this for a logistic map and you can see that, because logistic map is the one map, a discrete map, which actually have the wide variety of nonlinear properties exhibits, right? So there is a chaotic properties also exhibits for certain value of the parameter in the logistic map. So there you can actually study this and you can actually quantify that. So using classical Fisher information. So we actually then extended that one to quantum Fisher information in linear and nonlinear periodic system and found that quantum Fisher information was able to capture the dynamic behavior correctly. So we have done this for a certain models, the Dick model and Kerr-Medium, this kind of models. And we found that the Fisher information can be used to study the quantum chaos. So usually the quantum Fisher information for a given Hamiltonian is larger for chaotic region as compared to the regular regions. And this has an inherent connections with the average path length of a recurrence network that is recently be used to study. So there was some study on the recurrence networks, okay, to find the average path length. So that study can be, because this quantum Fisher information on that can be carried out. So numerical studies also suggested that ergodic property of the quantum Fisher information time series can be used to study chaos. So our study suggests that Fisher information can be used to study quantum chaos. That is one of the important result we have. So I am not getting to the calculation because that require another 1 hour discussions. So just one hint is that one quantum Fisher information can be used to quantify the chaos in quantum systems. And the other one is what we studied earlier, the average value of the observables, and the time series can be used to quantify the chaos. So the other well-known theory is the random matrix theory, and which actually developed by Wigner and Dyson to understand the spectra of complex atomic nuclei called random matrix theory. RMT can also be applied to many particle systems that do not have a classical counterpart. Several one-dimensional lattice falls in this category. So this is because the chaos has been studied for a quite long time in quantum systems, But the study in multipartite systems, if you have a linear chain, lattice, two-dimensional lattice, all these things. So studying in that is actually something we have to now carry out. So random matrix theory can be applicable to this, but there are some drawbacks for the random matrix theory. So if random matrix theory says that if the quantum systems whose spectra exhibit Wigner-Dyson statistics are actually chaotic. And so just a small hint about the theory. So consider a 2x2 symmetric matrix from ensemble of Gaussian distribution, and you have a Hamiltonian like this. And if you find the statistics of the energy difference between two levels, E1 minus E2 omega, and that P of omega looks like this. And that one is this. So basically, the level statistics will tell you, that is basically the random matrix theory you are getting, whether the system is chaotic or not. So if it obeys the Wigner-Dyson statistics, then it is a chaotic. If it is a Poisson statistics, it is an integrable. Okay. So there is a very Tabor and Bezier conjecture. So it says that for Berry-Tabor conjecture, quantum systems whose classical counterpart is integrable exhibit Poisson statistics. So if a quantum system, suppose, see, all quantum systems, you will not be able to find out the classical counterpart. Okay, suppose there are certain quantum systems, you can find out the classical counterpart. Then if the statistics, this RMT statistics shows a Poisson statistics, then it says that that quantum system is integrable. So, and Bogigas, Ginanoi, Schmidt conjecture, Bezier conjecture, the eigenvalues of a quantum system whose classical analog is fully chaotic obey the same universal statistics. So it is the eigenvalues actually obey the universal statistics. Basically, it is having three different types of ensemble: Gaussian orthogonal ensemble, Gaussian unitary ensemble, and Gaussian symplectic ensembles of level spacing as predicted for the eigenvalues of Gaussian random matrices depending on the symmetry of the Hamiltonian. So that is what from the RMT. And so the analysis of RMT, basically, if you take an observable and you can find out the average of that, right? And you find out the average that can be written as this. And so what you can see, the O bar is the average of O, okay, of that observable in some basis. So the matrix elements of OMN is actually proportional to this. So this is the random matrix theorists tell you. So this is actually the fluctuating term. This can be considered as zero for a long time when the system is evolved to long time. So now the RMT is very clear regarding the statistics and when is chaos and when is not chaotic. Now, but there are some drawbacks. That is that because the random matrix theory does not talk about different energy regions of the space. It only discuss about the energy level differences. And so thermalization necessarily implies a loss of information. So then we can have a different theory that is based on the thermalization property. We can actually identify whether there is a chaos or not. So what is a thermalization? Necessarily implies a loss of information of initial conditions. So so when the system evolves and under some Hamiltonian, and later on, if it loses the information about the initial condition, that is basically the thermalization. So the long time average of an observable in those cases becomes the ensemble average. So it was microcanonical ensemble average. So it allows us to make predictions about the behavior of complex quantum systems. So thermalization of a system. So eigenstate thermalization hypothesis based on the RMT, which has place chaos. So we will see that. So ETH is a well accepted tool for quantum chaos because this is actually an hypothesis, so it's not completely proven. So, but it actually give a very clear idea about the chaos in the quantum systems. So this is basically regarding the thermalizations. So the long time average of an observable, you can actually split into two terms. One is the diagonal term and other one is the off diagonal term. And when time goes to very large, you can actually show that this off diagonal terms goes to 0. So then the only the first term exists. Okay. If there is a thermalization happens. And so now you can actually substitute whatever from the RM theory, for a small fluctuations, you can actually substitute this one for OMM in the thermalization average, and you can see that it is just O bar. Okay. So basically the long time average is nothing to do with the initial conditions. It is just the average of that observable at that time. Okay. So this is one important aspect of thermalization will giving you that important property. It does not involve the initial conditions of the system. Because earlier we have seen that our problem using the average values of observers, depending on the initial state, we are having a different kind of dynamics for a long time. And here the thermalization says that if the system get into the thermalized state, it does not depend on the initial, it does not have any information of the initial values. So these are the drawbacks of this RMT. So it is independent of energy because it just talk about the energy level spacing, right? And how much closer states are within the energy window. So how these energy levels are close to each other. Okay, if these kind of things the RM theory does not address. So the eigenstate thermalization hypothesis, that is another important things which will help us to understand this chaotic property in a better way. So here what happens is you consider different energy windows, and actually these are narrow energy windows. So you will have so many because these are like so many energy windows one side, then again so many energy levels. So they are clubbed together and packets of that. And so for a given, if given packet of energy levels, and the energy levels are very close to each other, and if you find the OMN, that is for some observables density matrix elements for that given energy window alone. Okay, so if you find that can be approximated using this, because E bar is the that for that energy window, that average energy. Okay, because they are all very close to each other, that energy. Okay, and so that can be approximated by some smooth function of O of E and F of E. And here, what we can say that this, because earlier you had to consider an observable and corresponding random matrix theory to understand the chaos, and statistics based on that. So here energy thermalization hypothesis will actually, for each energy eigenstates, that means energy regions, you can talk about this chaotic properties. That is the main idea here. And to help that, okay, so you can have a adiabatic gauge potential to do that thermalization. And so the adiabatic gauge potential, I'm not getting to the theory here. So the adiabatic gauge potential, actually what the main idea here is, with that additional term in your Hamiltonian, you can make your system getting into the thermalized state. Okay, so for that you have to find out this A lambda operator, and you have to find the adiabatic no. Then you can actually analyze the system. So adiabatic gauge potential make your system to go to the thermalized state. Okay, and using this energy thermalized eigenstate thermalization hypothesis, using the adiabatic gauge potential, what we can show that this the norm square of the adiabatic AGP norm goes to proportion to D, where D is the dimension of the system for a multipartite system. So that is what our aim was. So in the multipartite system, because for example, a linear chain of atoms, there are suppose n atoms. So you actually find out this adiabatic potential A lambda square, that the adiabatic norm square, that then if you plot that versus the dimension of that linear chain, because linear chain means the dimension is the number of lattice points. So if you increase the lattice points, if it goes as that dimension, then we can say that system is chaotic. So this is one of the important thing we are now looking at, and we have some interesting result coming into that. So if the norm of the adiabatic potential adiabatic AGP goes as the dimension of the system linear, if that is linearly dependent, then we can say that there is a chaos. So because doing chaos in understanding chaos in the multipartite system is a very difficult scenario. And for that, the one now right away, our group is working on this AGP norm and to understand the system better. Okay, so we have some initial results, but I'm not presenting those results here because that again requires some other a long time to understand, explain. Okay, so I have described different ways to understand chaos or chaotic properties of quantum systems. For simple systems, the observable average can help you directly. But when you get into the multipartite systems, that may not be, because multipartite system, so under the subsystems which you consider is very crucial. So if you trace out the other subsystems, then it may not look like a multipartite. So you need a better theory for that. So that is these two, using Fisher information and the AGP norm, we are now trying to understand the chaos in the multipartite systems. So with this, I'll stop now. Thank you all.
Thank you, Dr. Chethil, for this very nice talk. So we can now open up for some questions.
I have one question.
Yes, sir.
Thank you for your talk. What kind of new physics or information one can extract or expect from a chaotic quantum system?
Okay, so the physics, if you look at, say, when you're talking about the quantum information, so all these non-classical phenomena, whatever we discussed, like entanglement, squeezing, non-classicality, all these features, okay, phenomena in quantum system, they're all very much crucial for our quantum computing or quantum information or this kind of aspects. So understanding the quantum chaos will definitely help you how those parameters, suppose, see, using squeezing nowadays, the quantum communication is happening, and that is one also quantum sensing is happening. So suppose if the system is chaotic, whether this can really help you to have a good sensing capability for that quantum sensor. Similarly, entanglement, whether the chaotic property. So there is also another studies, because I did not discuss that, the relation between the entanglement and the quantum chaos. So obviously entanglement is a very important physical property for a quantum systems. So all these things are related. Okay, so non-classicality, entanglement, squeezing with the quantum chaos, it is related. That is what entanglement versus the time graph. I showed you that you can see that depending on the state, how they are entangled with each other, the system is moving away from the regular orbit. Okay, that means if you have more chaos, you have more entanglement. That is what we are, in principle, we are able to see. Okay, so that way it's multi, because so many levels, so many physics are physical quantities are related to this chaotic properties of the system.
Thank you.
Yeah, I have a question.
Yes, Professor.
Yeah, see this, there was if you remember, I'm specifically asking you because you are familiar with it probably.
Okay.
That, this cat state, kitten state, this application to metrology, Jurek had a paper. Okay. And there he has pointed out that if you take sufficient number of superposition,
okay,
this system will go towards quantum chaos.
The
reason is basically, this interference effect between various cat states, in a controlled way can lead to quantum chaos. If you see that 2002 Nature paper, he has described that.
Okay.
Is it possible, now that you are telling, is it possible to sort of starting in a superposition of, because I have heard in Weizmann Institute, they have created 1,000 cat state superposition.
Okay.
So is it possible sort of to imagine in a controlled way, go towards quantum chaos and test out what is valid in classical, what is valid in quantum?
Yes, definitely we can do that. I think that study has to be done. And so basically, see, when you when you add the more states, means basically more number of wave packets are added together, right? And that is leading to, see, you remember the other calculation we have been doing when you are adding states, the squeezing properties, there is a chance that it actually disappearing the squeezing property. Okay, so here we have to understand this aspect. Obviously, we can have a study on that, because I cannot comment anything now, because that obviously this our AGP study, this adiabatic gauge potential and using that, because that is one, because multipartite systems definitely that will help. So I will look at that paper and see whether we can do something on that. Okay.
Any more questions?
Can I ask one more question? So, sorry.
Yes, sure.
What is the, in one of your slides, you mentioned about characteristic time. So could you please explain what is the characteristic time scale of the problem? I mean, definition, something.
Can you tell me which, when I was mentioning which part I will discuss that?
I think your slides was not numbered, so I can't remember. Maybe
that is the area wise, because I was discussing
in the starting
regarding the random matrix theory.
Before that,
because there was a relaxation time I was discussing, as I pointed out, and but not characteristic time. I can share and we can.
I think before, in the starting, maybe
okay,
after third slide or fourth. It's a minor question, so I can ask you through the email. So
okay, you can please. Yeah, because you can ask that, because I don't remember. I put some characteristic time. There is a revival time I put somewhere, and then also a relaxation time. So okay.
Mm-hmm. I mean, how you do you define the characteristic time scale? So it was very important for me. So I will then ask you.
Because you have my email ID, right? So we can actually have a discussion. Okay.
I don't have, but internet will help
I can
me.
actually share it here in the chat.
Thank you.